for the subject are the Polchinski volume 1 and 2, mostly volume 1, for what we're going to discuss in the lectures. You also get lecture notes that follow quite closely the contents of the lectures. So strain perturbation theory, as the name suggests, it describes perturbatively the dynamics of strings, so relativistic strings. So whenever you're doing a calculation in strain perturbation theory, say a scattering amplitude, you start with some free answer, with the answer which you'll get in a theory of free strings that don't interact with each other. And then you introduce some interactions. And you write down a formal power series which corrects the free answer systematically, order by order, in some parameter which describes the strength of the interactions. So this is completely analogous to what you would do to study quantum field theory in a perturbative way. So if you're scattering amplitude in quantum field theory, you start by describing the motion of some free particles. And then you add systematically some interactions. Now, a basic difference is that quantum field theory usually you also have some, possibly it's formal or not, non-perturbative definition of the theory. I mean, a bit formal, you could think about a path integral over some fields. So, we have some free action plus a correction. And then by systematically expanding in powers of the corrections, you can get the actual perturbation theory. So we do not know what to put here. So the basic difference between string theory and quantum field theory at this level is that quantum field theory is usually thought as something well-defined, with non-perturbative definition and with some perturbative expansion. In string theory, we have essentially no clue on how to give a general non-perturbative definition of the theory. We only had the perturbative expansion plus some extra information that I will discuss later in the lectures. So you might be surprised that you could have a perturbative expansion for something without having the thing itself. But even in quantum field theory, you don't really need to start from a path integral in order to write down a perturbative expansion. If you try to write down an S matrix which contains some particles with some basic interactions, and you impose constraints such as unitarity, you can systematically build up a perturbative expansion without having ever heard about a path integral or a Feynman diagram even. Of course, the right-hand side is not an actual answer in the sense it's a formal power series. It doesn't converge, it's asymptotic. There is a whole industry trying to understand to which degree does a perturbative expansion define something. There are some very interesting topics, such as resurgence, which are connected with understanding this question. But at least, naively, this is just formal. I mean, if your coupling is small and if you sum up a certain number of terms, but not too many, you can get a number which is pretty close to the true number. So clearly, this is not a full definition of a theory. So just to give a picture of what sort of typical processes are described in perturbation theory. Well, in quantum field theory, your typical perturbative process involves a bunch of particles which come in from the past and from far away, come in some region of space-time and start interacting with each other. interactions happen at some discrete points in space-time, or something special happens. And after a bunch of interactions, the particles then propagate freely and go back at infinity. In string theory, you would like to to write something very similar. Except that the basic particles are replaced by strings. So instead of having a point-like object that describes a line in space-time, you want an object which has one dimension in space and describes a tube, a worksheet in space-time. Now, in principle, I guess you could try to now add interactions where special things happen. But actually, I don't think anybody knows how to do that in a good way, and it's not needed. A nice properties of strings is that they come with the natural interactions. You don't need to add by hand an interaction vertex. You just require the strings to smoothly join and separate out again. I'm not very good at drawing, but you should imagine a complicated surface. Perhaps there might be even loops. A complicated surface where these cylinders come together and separate out again in a smooth manner. So a pair of pans is a typical picture of two strings coming together and merging into one. So we will spend a considerable number of lectures trying to make sense of this picture, to understand from how to make a picture like that into something concrete, into the actual perturbative expansion of string theory. So, do you have any questions about what does it mean to have a perturbation theory? Most of you, I guess, encountered quantum field theory quite recently, and probably perturbation theory for quantum field theory is all that you've seen of quantum field theories until you did some conformal field theory.
How do you define a string theory then, with the couplings and the free part, or what do you define when you're defining the theory?
Well, first we'll have to decide what does a relativistic string look like, a free relativistic string. And then we try to introduce interactions which describe processes like this, where a certain number of these strings come together in a region of space-time and then go out again. Now you put a certain weight which controls the strength of the interactions. You try to write a prior series which satisfies unitarity.
When we're talking about strings, do we always mean closed loops?
I will mention later the alternative open loops. But yes, at the very beginning, when you define string theory, you think about closed loops. So there is no special point on the loop. Okay. So now strings come with an intrinsic dimensionful quantity, which is somewhat analogous to the mass of a relativistic particle. So this dimensional quantity, the tension, gives you a scale, an energy scale. The inverse of what's called the string length. This scale determines sort of the energy scale of the internal vibrational modes of a string. A string, being an extended object instead of a point, has a lot of internal degrees of freedom. It can vibrate in various ways. You can think about, very roughly, these vibrational modes as a whole bunch of harmonic oscillators, one for each mode. And the energy of these harmonic oscillators is controlled, the energy it takes to excite harmonic oscillator, so it's controlled by this length scale, by this energy scale. So if you look at it at the string at energies much lower than the string scale, very few of these oscillators are excited. The energy looks like a point-like object with just a small amount of vibrational modes turned on. This is really true for every extended object, right? Every object with internal degrees of freedom. If you take an atom or a molecule, look at very low energy, it looks like a point. Then if you start giving energy to it, you can excite some vibrational modes, and the properties of this point-like object seem to change, right? So you might, the same molecule, the same atom, at low energy might look like many different point-like objects depending on which internal degrees of freedom you have excited. And the same is true for strings. Of course, if you give enough energy and you excite enough these internal degrees of freedom, you will start seeing them. For a molecule or for an atom, if you give enough energy, the atom will just break down into the elementary components. But a string is itself elementary, so you just start behaving in a different way from a point-like particle. So if I draw a sort of an energy diagram, at low energy, you get a tower of particle-like modes. So each string gives a tower of particles corresponding to different excited modes of the string. And string theory looks like a quantum field theory for all of these particles, because the strings look like points. But as the energy goes beyond the energy scale of the strings, then you really see strings. And their behavior becomes completely different from the behavior of particles. This has a variety of consequences, which I will review momentarily. Now, any questions? So the very first striking fact that we will notice when we study this type of particles is that although there is a scale, the lowest levels of this tower, the lightest particles in this tower, are actually massless. Well, we're going to do bosonic string, for which the lightest particles are actually tachyonic, and we will ignore them. But if you study a well-defined theory of strings, like superstring theory, the lowest particles in the tower are massless. And not only they're massless, they are very interesting massless particles. They're gravitons. So inside this type of particles, you get gravitons. So this is the foremost reason we are interested in string theory. String theory is, among other things, the theory of gravity. At low energy, at least, string theory has gravity. But because the behavior of strings at higher energy is much different from the behavior of particles, you do not get UV divergences. So one of the basic consequences of having these discrete interaction points in quantum field theory is that when these interaction points come together, you get divergences. Because strings are not point-like and interact in a diffuse way, they have a much better UV behavior. Another example, if you scatter a particle from another particle and you go at high energy, you get particles that scatter off at very large angles. Right? Particles have hard cores. That's how you find particles, how Rutherford found that the nucleus was a particle, right? It is. You shoot some probes at it, and they bounce off at large angles. On the other hand, because strings are fluffy, they sort of pass through each other if the energy becomes large enough. Instead of the probability of bouncing off growing and growing, sometimes diverging, as it happens with particles, the probability of a string bouncing off another actually decays exponentially fast once the energy starts becoming large enough. So which means this string perturbation theory is free of UV divergences. Mm-hmm.
Should we expect that these effective QFTs will be renormalizable or perturbatively renormalizable?
No, they will not. So the point is that the UV divergences are cut off by the string length. So this quantum field theory is an effective low-energy quantum field theory with a whole bunch of non-normalizable interactions. It has higher spin particles too, which automatically tells you it's not renormalizable. So it has particles of all spin, gravitons. Not just gravitons, they have spin too, but there are massive particles of very high spin. But the point is that as the energy passes the string length scale, things become better behaved. So in that sense, string theory gives you a way to cure the perturbative problems of quantum gravity, which is different from saying that it cures all problems of quantum gravity. But it's nice, and it's the other reason we study string theory. So within string theory, what happens is that right. So I want to say, suppose you're trying to define a theory of quantum gravity. Okay, what sort of things can happen? When do you know that things are going to surely break down? That's right. So if I have gravity and plus quantum fields, I know pretty much for sure that at the Planck's, well, with reasonable certainty, there are discussions about that too, that above the Planck scale, I had to replace it with something else. Because, but by the time I get here, things will start diverging very badly. And it's perfectly possible to imagine scenarios where things indeed change at the Planck scale, where I have gravitons and quantum fields all the way to the Planck scale, and then something happens. Even within string theory, there's something called M theory where that happens. In M theory, the simplest example of M theory discusses something like 11-dimensional supergravity all the way to the Planck scale, and then at the Planck scale, something unknown happens. But string theory gives another possible scenario. It tells you what could happen is that you have gravity. And when I say gravity, I really mean perturbative gravity. So I should stress, gravity, so you hear that there are troubles treating gravity as a quantum field theory. There is no problem treating gravity as an effective low-energy quantum field theory, perturbatively. The problems start when you try to make it non-perturbative. Anyway, so you have perturbative gravity. You know that something will have to happen before the Planck scale where it becomes non-perturbative. But in principle, something could happen way earlier than the Planck scale. So you could have some lower scale, that here is the string scale, where perturbative gravity is replaced by something else still perturbative. And then that new perturbative thing will have to be replaced by yet something else when things become non-perturbative. But whatever problems you encounter here in this scenario will have nothing to do with the sort of problems you'd encounter in this scenario. Right here, you worry about things like quantizing space-time, say. In string theory, by the time you get here, space-time has changed into something quite different, or start behaving in a way that is very different from quantum field theory. So you will encounter different questions when you try to give a non-perturbative definition of the step. Now, it's not known if string theory is the only theory that gives this sort of solution to gravity, but it seems likely from a variety of theorems that whatever perturbative solutions of perturbative completions of gravity you can write down, they will have properties similar to string theory. For example, there are theorems that say that no finite collection of particles can cure perturbatively the problems of gravity. So whatever you do here will have infinite hours of particles of arbitrarily high spin, and so on and so forth. So it will pretty much look like a string theory. Okay, so these will be the topics of at least this week. We'll try to understand the spectrum of particles that we find in a string theory. I don't think we'll be able to show that string theory. No, we will not be able to show that string theory is free of UV divergences. But we'll at least try to give a reasonable, intuitive explanation why that should be the case. Now, what we'll be able to see, though, is some very interesting properties of string theory, which are sort of the second reason we find it interesting. So, in a quantum field theory, you make all sorts of choices when you define your theory. You choose which particles you put in your theory. You choose which interactions you put. If you're treating gravity classically, you pick the metric you're coupling in quantum field theory to, and so on. And naively, similar choices are made in string theory. At the very least, you get to pick the value of the coupling constant. Okay. But when you start studying the perturbation theory, you discover something striking, that for each parameter you put in your theory, there is a massless excitation which describes fluctuations, dynamical fluctuations in that parameter. So at the very beginning, we'll take our strings and couple them to some background metric. But then immediately we'll find a graviton, which describes fluctuations of that background metric. We'll find a scalar field called the dilaton, which describes fluctuations in the coupling. And this theme sort of continues to hold true. Whenever you try to put a parameter in your theory, it becomes a dynamical quantity. And as you progress further, even discrete choices that you made turn out to be dynamical. So this is very nice, and it's also terrifying. So it's very nice because it tells you that whatever you're trying to define is quite unique. We don't have a variety of perturbative string theories. There is just one perturbative string theory. You might hope that this unicity keeps holding to the underlying theory. So if you have this dream that quantum gravity is so hard that there is probably just a unique way to find a theory of quantum gravity, there is a unique possible theory of everything because it's a very hard problem. Well, this would seem like a dream come true. Here there is a theory which is so rigid and unique and includes gravity. Now, the problem, though, is that all of these choices became dynamical, which means dynamics is very important. So the other lesson that you get is that, well, the universe can look very, very different depending on dynamical processes. The same underlying set of laws might give you completely different low energy dynamics. And which dynamics you get at low energy depends on dynamical processes, boundary conditions, initial conditions of a universe, and so on and so forth. So string theory, rather than saying, oh yes, go for it, you can bootstrap the theory of everything from some low energy observations of the universe. String theory tells you, no, I'm sorry. There is just, it's not possible. The law of natures are just, in string theory, the law of natures you see at low energy will be just determined by something, by dynamic mechanism. So in particular, string perturbation theory just allows you countless different ways to realize semi-realistic universes within it. And it gives very little guidance on what non-perturbative dynamics might actually select which universe is described by string theory, and to which degree it's a matter of initial conditions or a matter of intrinsic property of the theory. So sort of string theory gave us this harsh lesson that it's right. Even in a unique underlying theory might not give you a unique set of low energy laws of nature. So now clearly understanding what is this question mark, what is a non-perturbative theory underlying string theory might help. But it's still a hard dynamical question. So I would say that the biggest problem in string theory is understanding if there is a non-perturbative definition, problem one, and problem two, try to figure out what kind of universe would such a definition give you, and how much the low energy universe depends on boundary conditions, initial conditions, or whatever that means. We really even lack the language to describe the problem properly. And the funny thing is that, so at the end of the lecture, I'll give a few words about holography. Holography gives a non-perturbative definition of string theory in some backgrounds, which don't look like our universe, but they look like universes of negative cosmological constant. And amusingly, you get different non-perturbative definition of the theory depending on what is the large-scale structure of the universe. So I find that very disturbing, because it suggests that there is some kind of there are some deep connections between the large scale, what happens at large scales in the universe, and what are the microscopic laws. Right? We have this sort of idea that we derive from quantum field theory, that you write down the microscopic laws of the universe, and then you do some hard calculation, and you find out what's going on at long distance. But even that idea is not obviously true in a theory of quantum gravity. Mm-hmm.
What do you mean by the large-scale structure of the universe?
Well, those universes with negative cosmological constants are like a universe in a box. There is sort of a boundary at infinity where you get to decide how things look like, and then it evolves in.
So what the boundary is.
Decide how the universe looks like near the boundary. And different choices give you different non-perturbative definition of the theory through holography, which is disturbing. Anyway, so going back to the topics of the lectures. So after we define string perturbation theory, in the subsequent weeks, we'll discuss some other topics, which are D-branes, dualities, and supersymmetry. So D-branes provide the answer to the question that was asked a moment ago about, do I only consider closed loops of string? So, as I said, there is not much freedom to modify the way closed strings interact and behave.
Do we care about orientation of strings? Or?
You can. There are variants where you don't. We will not discuss unoriented strings, but it's possible to discuss them. Now, so one way to put extra variety in string perturbation theory is to allow the strings to have endpoints. So that you don't just have closed loops, but you have also open lines. And the same way as in a quantum field theory, you can put different particles. Now you get choices. The endpoints of a line look like points, and it turns out you can put a variety of choices here which are analogous to choosing different particles in a quantum field theory. And then as they evolve, these boundaries sort of propagate out. And here really my drawing skills will be put to the test. I already know I'm going to fail this test. But you can imagine drawing surfaces which have boundaries. Let me see. Okay, so you should imagine these as sort of flat sheets, right? And then a cylinder can be smoothly connected to a flat sheet. And okay, you can imagine drawing a surface which smoothly interpolates between these lines and these tubes coming out.
So do the tubes interact with the sheets?
Yes, smoothly. So you just write some two-dimensional surface which joins together the tubes and the sheets in whatever topology you want. So this gives you a theory of open and closed strings. Yes?
I still don't understand what do these different colors mean.
So they just describe different ways a string can end. Let me give an example. I could say that the orange color means the endpoint is free to move in space-time. The blue endpoint might be endpoint is constrained to belong to some line in space-time. And maybe this purple endpoint is constrained to lie inside a surface. These are just some examples. It's just a different, each color corresponds to some different rules on how this endpoint can behave. And for every pair of such rules, you get some tower of open string modes, some spectrum of open string modes, which depend on the rules that you are using. Yes?
Is that spectrum generally discrete or continuous? Or?
Much as the spectrum of, I mean, when I say spectrum, I mean that you get a low energy, a tower of particles with some masses which are discrete values. Typically, there are just multiples of this. So for example, you might have massless particles. It's very common for open strings to give you gauge fields, for example. So D-branes are one of the natural ways you can introduce gauge fields in string theory. I mean,
even when we have these point-like bits now, are we still free of using divergences?
That's right. Because I put the points, but I did not let them, I did not introduce interaction point for these boundaries. They just go and do their own thing. All interactions are controlled by the bulk string, by the sheet. Right? So this is still free of divergences. It has all the good properties of the string theory, but it has extra towers of particles. Okay? If I do something like this, some of the massless modes, well, actually, right, so I said string theory makes every choice dynamical. So this happens here too. For example, say I have the endpoint, the blue endpoint is constrained on some line in space-time. Well, you will find a massless open string which describes fluctuations of this line. So automatically, these objects that I'm introducing, these rules I'm introducing, become dynamical objects called D-branes. So each of these rules become one new object I put in my theory with degrees of freedom, which is very massive and slow moving, and with degrees of freedom are described by the open strings. So this is interesting because it means that, again, what you thought was your choice, do I put a D-brane or not, actually becomes dynamical. Because these are dynamical objects now, they can even appear and disappear from nothing. They can be created or destroyed by quantum processes. They can be pair-created. And indeed, you can even find strong hints that the original theory of closed strings secretly had to have the D-branes all along. You can try to, for example, you can try to put string theory on some slightly singular gravitational backgrounds where there is some cycle of space-time which is very small, and you would get naively a divergence in perturbation theory as the cycle becomes very small. But you discover that that divergence really looks like you had integrated away a D-brane that was wrapping that cycle. So there is strong evidence that these D-branes are just one unavoidable ingredient of string theory. So that when I write this graph, right, at some point, at some other scale, which I could quantify, but I prefer not to do. I mean, it's some intermediate scale between the string length and the Planck length. You'll start have strings and branes. D-branes. And then, who knows? So this is so when you start looking at this, you sort of realize that strings, that string theory is not exactly theory of strings. All that was really happening is that whatever was the underlying theory, the lightest, in this regime of parameters where the string theory is perturbative, the lightest objects are strings, and there are other heavier objects. And in some magical way, the dynamics of the lighter objects seem to be automatically producing the behavior of the heavier objects. Now, do you have any questions? So again, this sort of reaffirms the notion that string theory is rigid. You don't get to decide what are the ingredients you put in your string theory. But also because of something called dualities, branes are a very important ingredient in showing that. Well, let me say this properly. So we'll start defining superstring theories. We'll find discrete choices which are very basic. So when we start defining superstring theories, we'll define something called type 2A string theory. We'll define something like called type 2B string theory. We'll define or things called heterotic string theories. So each of these string theories comes with its own interaction strength, which is a dynamical parameter, I was saying. Now, it turns out that there are some quantities which can be computed exactly thanks to something called supersymmetry. So they can be computed exactly as a function of the parameter. Often they just don't receive any perturbative corrections. So if you assume for a moment that there is an underlying theory behind your perturbation theory, you can use these protected quantities to study the properties of the theory. Sort of, if I describe so I can take the type 2A string theory and take start from a situation where the coupling of type 2A is very small, and try to make it larger and see what happens to these protected quantities. I can try to do the same from type 2B or for heterotic strings to get sort of families of theory, well, more like families of dynamical backgrounds for these theories where the coupling is larger and larger. As I do that, it happens that the branes become lighter and lighter. So the mass of the branes goes to infinity when the coupling is turned off and behaves like essentially 1 over the coupling. So as I proceed in, things start becoming more democratic as the branes start having masses comparable to the masses of the strings, to the tension of the string, masses of tensions. And at some point, as the coupling is increased all the way to be larger than 1, some of the branes might even become lighter than strings. The degrees of freedom of the theory really reorganize themselves, and we can only follow those very small pieces of information which are protected by supersymmetry. But those pieces of information remain sensible and actually start looking a lot like the pieces of information of other string theories at weak coupling. So as you start filling in, sort of mapping the space of possible configurations by looking at these protected quantities, the various features start joining in. And you also find completely different regions which are not string theories, but they are less well understood things like M theory. Mm-hmm.
Sorry, so say, I think I misunderstood this. So say if you start with type 2A,
Yes.
the low coupling, and then you gradually make the coupling bigger.
Yes.
I heard that it now shows properties similar to, say, type 2b with low coupling again, or again?
Right. Or, yes, roughly, but with low coupling. So I think the statement is cleanest for type 2b. If you take type 2b theory, so there are a variety of things you can do to the theory. If you just keep it, so and I don't want to get into details now because I want to discuss a little bit something else. But so there are a variety of things you can do. You can play with the coupling. Sometimes you can play with the geometry of space-time also, sort of make parts of space-time smaller or bigger as you change the coupling. So there is a variety of manipulations you can do. And you can sort of push the theory in all possible directions. And no matter in which direction you push the theory, you land on something which, as far as these protected quantities are concerned, looks sensible and can be often reached from some other theories. So the space of dynamical configurations which can be probed by these protected quantities seems to be just connected. So that's why you talk about a string theory instead of talking about type 2A string theory, type 2B string theory. So as whatever is the, yeah, okay. Right, so this gives you some evidence that there is sort of an underlying structure which you can call string theory, you can study, which manifests itself in these perturbative string theories in various regimes. And deep branes are very important to sort of give support to this picture, because a lot of the degrees of freedom you need to keep track to compare different string theories come from deep branes. So the relations between different weakly coupled string theories are called dualities. And they're a very rich topic. They really taught us that the degrees of freedom of a theory can get reorganized a lot as you change the parameters, or even dynamically. And indeed, we learned a lot of dualities in quantum field theory, starting from dualities in string theory. So string theory and dualities in string theory have been also a powerful tool to study quantum field theory. Because sometimes the degrees of freedom of, well, you can sort of engineer quantum field theories as the theories that live on some deep branes. And then as the degrees of freedom of the string theory get reorganized, the degrees of freedom of these quantum field theories also get reorganized in a nice manner. And sometimes you can sort of decouple this reorganization from the reorganization of the overall theory. You get quantum field theory statements. Now, so I mentioned supersymmetry. Let me say a few words about that. So what is supersymmetry? Supersymmetry is a symmetry which relates the fermions and the bosons in your theory. So supersymmetry is not a necessary property of string theory, but it helps a lot in studying the theory. So supersymmetry in general helps studying theories because the symmetry between bosons and fermions sometimes allow you to cancel quantum effects. Essentially, bosons and fermions give opposite contributions when they run in loops. And if in some questions, supersymmetry guarantees that this contribution cancel out. So in supersymmetric theories, you often have some degree of protection from quantum effects for certain quantities. For example, so I said that the coupling of the string theory is dynamical. So that means in absence of supersymmetry, you have just what the value of the coupling is a dynamical property, and it will go somewhere depending on the dynamics. And there is typically does not remain small. So when you try to define a non-supersymmetric string theory, you just have a perturbative definition, but if your perturbative dynamics tries to make the coupling larger and larger, clearly you lack self-consistency at a very basic level. In a supersymmetric string theory, you have some control that allows you to say that it's self-consistent to think about a weakly coupled theory, because at least in certain configurations, you can guarantee that the coupling will not run, and will not dynamically change. So although in principle you can define non-supersymmetric string theories, supersymmetric string theories are the only ones we know how to study, pretty much. And for supersymmetric string theory, we can make a variety of interesting statements. Now, there is also a close relationship between supersymmetry and the cancellation of UV divergences, in the sense that in supersymmetric string theories, the fact that there are cancellations between bosons and fermions is part of the mechanism that cancels out some of the UV divergences. But again, it's not, in order to cancel out UV divergences, you don't strictly need an exact cancellation between bosons and fermions. So that's what I'm saying. Supersymmetry is a useful property to put on top of string theory. It appears naturally in the string theories we know how to define. It's not a necessary property of string theory. So most of the lectures will be devoted to something called bosonic string theory, which has no supersymmetry, but it's simpler. It has a tachyon, it's not self-consistent, but it's a very good toy model. And then in the last week, we will introduce supersymmetry and define the superstring theories. Okay. So I mentioned dualities, debrane supersymmetry. Right. Now I want to say a few words about ADS-CFT. So we're not going to do any ADS-CFT in the course, but today's lecture is mostly about giving you a picture of where string theory lives within theoretical physics. So I need to mention ADS-CFT. So let me go back to D-branes. So I said that D-branes are heavy objects. Now, because string theory is a theory of gravity, you might immediately worry that if I put a very heavy object in the theory of gravity, it will have a very large back reaction. So you might wonder, how could it be perturbative to put a very, very massive object? But it turns out that the mass of D-branes is sort of in a nice intermediate regime. So they are light enough not to back react with coupling, and yet much heavier than strings. So if you write the coupling as, if you write your coupling as, let me say this properly. Right, suppose that you write, in quantum field theory, you write your coupling as 1/g² in front of your action. Then something like a solid on your quantum field theory will have a mass that goes like 1/g², right? And something that has mass of order 1/g² is something which will also back react a lot in the theory of gravity. But D-branes have a mass of order 1/g string instead of 1/g². So they have a mass that it's sort of, in the logarithmic scale, is really intermediate between the string scale and the Planck scale. Now, suppose now that you take, so in a sense, the back reaction of a D-brane is still proportional to the coupling. Not to coupling squared, but still to the coupling. It's still small. Now, suppose I put many D-branes on the same spot. Then the back reaction will also have and will be proportional to the number of d branes. And you can imagine looking at a regime where you put a lot of d branes, where n string is finite. So that should give a real back reaction to your background. And now you can sort of do two things. You can study closed strings plus open strings with n d branes. Or you can study just closed strings in the back-reacted geometry. I mean, very roughly, you can think about putting together a lot of d branes that will make a black hole. Now you have a black hole geometry. You can try to study perturbative closed strings in the black hole geometry. Right? Now, these two things are trying to describe the same process, the same situation. So somehow there should be some equivalence between the two. There should be some way to say that a theory of closed string in a finite background must be the same as a theory of open strings, of closed strings plus the open strings that live on n d branes. This is called open-closed duality. So what Maldacena did was to realize that you can take a decoupling limit where most of the closed strings go away, most of the open strings go away, and all that you're left with is the quantum field theory of massless open strings. Which is essentially a variant of UN Yang-Mills gauge theory. Well, some supersymmetric variants of UN gauge theory. We'll figure out how the UN comes about in one of the lectures. And the same limit on the other side sort of gives you just closed strings. In a background which is called ADS anti-de Sitter. Sort of a near horizon geometry of this black hole. And this is the very basic example of holography. It tells you that the theory of gravity and other things in a negatively curved spacetime can be equivalent to quantum field theory in a different spacetime. So this is very useful because this has a non-perturbative definition, among other things. Right? We feel we understand quantum theories very well. And inside there, you have embedded the problem of quantum gravity. This can be used both to learn more about the dynamics of this quantum field theory, large N, but also to give you a non-perturbative definition of gravity in this background. Now, holography was derived from open-closed duality, but holds on its own. There are presumably examples of holography which don't come from string theory, although I'm not aware of any. Meaning, there are a variety of quantum field theories which have a chance to have an holographic dual. Each of those holographic quantum field theories will give you some theory of quantum gravity in a negative curve spacetime. Now, these quantum field theories are typically strongly coupled and difficult to study. The ones we can study best are the supersymmetric ones, for which some quantities are protected and can be computed more easily. For those supersymmetric theories, what you find on this side is always a string theory or a theory or something like that. It's always some of these actors. it would be spectacular to find a quantum field theory whose dual is not a string theory, is not related to any of this. But we don't know how. On the other hand, holography sort of suggests very strongly that a lot of the properties of string theory will be shared by other theories of quantum gravity. For example, within holography, it's pretty much automatic that all the parameters become fields. All the discrete choices become dynamical. The different looking theories can be connected by dualities and processes like that. So there might be other blobs out there besides this, maybe disconnected from this, maybe connected in some non-supersymmetric way. But some of the lessons that you learn studying string theory presumably hold for more general theories of quantum gravity. At least if you accept the assumption that defining a theory of quantum gravity is something that you can do on different spacetimes. Again, there is always this troublesome or deep mystery of UV-IR connection, meaning there is always this open question: can I really define a theory of quantum gravity independently of what is the large structure of the universe? There's a question I don't know how to answer.
Mm-hmm. Is that only a problem with the negative space-time, negative curvature space-time?
Well, it's a problem that appears, so I think the most dramatic examples of this question are found in holography, but it's very likely that this problem holds for systems with positive cosmological constant too. I mean, so right, our universe seems to have a positive cosmological constant, or perhaps alpha very, very small. You could say my theory of quantum gravity just cannot be put in a situation with negative cosmological constant. And so it does not have to share any of the lessons or properties that can be derived from holography. Maybe that could be the case. It's sort of hard to believe that if you have a theory that has a vacuum with cosmological constant 10 to the minus 130, it's not possible to cook up some way to get at least a metastable vacuum or something which is negative cosmological constant. I mean, even the standard model, I think if you compatify it on a circle, you can get back of negative cosmological constant, just on the Casimir energy of the neutrinos, I think. Anyway, now just to say that, right, I cannot say for sure these lessons will hold for any theory of quantum gravity, but you'll have to work hard to avoid them. So you really have to have a theory which intrinsically does not accept the idea that of being put in a negative cosmological constant box. So you will, which means you sort of, well, anyway, I don't know exactly what it means, but right, I'm not giving you this course with the idea, oh, now I'm going to teach you what the universe looks like. This is a tool. It's a useful theoretical tool. It has some lessons. Some are harsh. Some are engaging and interesting. And I think you need to, if you want to study quantum gravity, you need to know these lessons one way or another. You have any questions?
In this decoupling limit where you recover the integral stage theory, are you recovering it in the sense that you get some perturbative expansion that matches every order?
No. So, right. So here you need to be in a non-perturbative regime. So the interactions of this theory are controlled by NG. So this theory, when it's strongly interacting, it's dual to closed strings or essentially gravity, closed strings in a weakly curved space-time. As you increase the curvature of space-time and you move away from gravity and into string theory, you might try to get with coupling here. So this equality is supposed to hold for all values of the coupling, in all n. But of course, because the right-hand side is defined perturbatively, this equality becomes the definition away from the perturbative regime. So here's something which is presumably well defined for all the choices of parameters. Here's something which is tentatively defined perturbatively. So when I say that they are the same, it means if I expand this perturbatively in the same compatible regime, I should get the same as this. And there has been a very intense effort to actually verify this statement. Pedro Vieira here is one of the experts in checking that this is indeed the case. And away from that regime, it gives you a definition of the right-hand side.
We had to match the repetitive expansion to relate it to the top one as well, like the closed open zebra.
So there is something called a Tooth expansion, which I will explain in one lecture. So here there are two parameters, n and g. You sort of get you can organize the expansion into, you can sort of do a 1 over n expansion and a g expansion, and play around on which you do first. If you sort of resum the 1 over n expansion, if you resum the gn expansion while remaining perturbatively 1 over g, in g or in 1 over n, then you get this perturbative expansion. So to get here, you need to sort of resum this expansion to a regime where this is finite, even though g is still small. So you have some functions of n and g, and you want to keep this fixed and large, while g is perturbatively small. But we'll look at it again. Any more questions? So today we had no formula. Don't get used to it. The very reason for having this initial lecture is to give you a big picture before we get into very nitty-gritty calculations. Many of the next lectures are going to be very technical. Your knowledge of quantum field theory is going to be pushed into unusual directions. You'll do things that might not have seen in quantum field theory. Although I understand you've done some quantum field theory, correct? So that will help a lot. I will try to do my best to not require conformal field theory, in the sense that most of the analysis I'll do only requires free field theory, because you use theories which are both free and conformal. And I invite you to sort of redo the analysis using conformal field theory in an easier way.